So we're going to investigate graphs of polynomial functions today. All right, so we're going to use the properties of what's called end behavior, which is what happens when x gets really large or really small, to analyze, describe, and graph polynomial functions. And then we're going to find max and mins. So end behavior tells us what happens with the graph as x approaches positive infinity or as x approaches negative infinity. So when we look at a graph and, okay, so we're going to see either the graph goes up to positive infinity or it goes down to positive infinity, but what's happening as the graph moves from left to right? And that's determined by the degree and the leading coefficient of the polynomial. Those two things determine what's going to happen when we're going down on the ends. So here are examples of polynomials of degree 1 through 5. We have linear, quadratic, cubic, quartic, and quintic. Now, look at the linear, cubic, and quintic for a minute, 1, 3, and 5. What do you notice about those three graphs? When we're going from, as we go farther and farther left and right, what do you notice about those three graphs? Anything specifically? The lines go up and down, okay? So if we notice that, okay, all right, so let's go with that. The lines go up and down. Now look at the 2 and 4, degree 2 and degree 4. How do those, look at them and then compare them to the 1, 3, and 5. What do you notice? Is there any difference in them? Do you see any difference in them? Or is it just a bunch of lines? Okay, all right, exactly. That's one of the things I was hoping you would notice. If you look at here, okay, degree 1, right? As it goes to the left, the graph goes down. If it goes to the right, the graph goes up. But and then that's what's, and so here it does that too. As it goes to the left, the graph is going down. It goes to the right, graph's going up. Left is going down, right is going up. And that's different than the even degreed ones, because the even degreed ones, they both go at the ends, they're both going up. This one goes up, that one goes up. So the odd degree polynomials, when we talk about what happens on the ends or the end behavior, one end of the graph is going to go to positive infinity, and the other end is going to go to negative infinity. When we're talking about even degree polynomials, they're both going to go the same direction. Either they're both going to go to positive infinity, or they're both going to go to negative infinity. But, so the degree, whether it's odd or even, tells us that much. Okay? If they're odd, they're going to go opposite directions. Okay? If they're even, they're both going to go the same direction. Okay? Well, then what changes which direction they go at the end, as far as whether it's positive or negative, depends on the leading coefficient. And here we have a table that tells us about that. Okay? So the first part here, it says the leading coefficient is greater than 0. So A is positive. So when the leading coefficient is greater than 0, then an odd degree polynomial is going to start at negative infinity and end up at positive infinity. So we have has it written out here. It says as x goes to, that little arrow there means approaches, as x approaches positive infinity, p of x, which is our y, means that that's going to positive infinity. And as x goes to negative infinity, p of x goes to negative infinity. And this is in your book too. So, all right. For the even degree, if the leading coefficient is positive, as x goes to negative infinity or positive infinity, then y goes to positive infinity. You can see they both go up. If the leading coefficient is negative, well, what happens when we multiply by -1? What do we get? Okay, we get the opposite, right? Okay, instead of a positive, we get a negative. Instead of a negative, we get a positive. Well, if the leading coefficient is negative, then these things are the opposite. Instead of this graph starting from negative infinity and end up at positive, it starts at positive and goes to negative. It is reflected vertically, right? Okay. Because that leading coefficient is negative, we have a vertical reflection. So as x goes to negative infinity, y, or p of x, goes to positive infinity. And as x goes to positive infinity, p of x or y goes to negative infinity. That's an odd one. And on even ones, they both go to negative infinity. Well, that should make sense to you because when we talked about quadratics, okay, even degreed ones, when the leading coefficient is positive, it smiles, right? And when the leading coefficient is negative, because when you're feeling negative, you frown. So then it goes down. Okay, so we're going to use those characteristics to be able to understand what happens with graphs then. So positive leading coefficient, we have two things that happen, depending on whether it's odd or even. Negative leading coefficient, then they're the opposite then. All right. So here they want us to identify the leading coefficient, the degree, and the end behavior. And when it says to identify the end behavior, all we're going to do basically is write what they have in one of these four boxes, depending on the situation we have. All right, so what's the leading coefficient for this polynomial? Okay, -1. All right, the number in front of the largest degree is -1. Okay. And so the degree of this is 4. Okay. So we have a negative leading coefficient and an even degree. So that means then our end behavior is going to be this bottom right-hand corner then. So it means then that this graph is going to look something like this, possibly. So that as x goes to the left, goes to negative infinity, y goes to negative infinity. And as x goes to the right, positive infinity, y goes to negative infinity. So we'll say then that as x approaches negative infinity, then our function is q of x, then approaches negative infinity. All right, that means as it's going to the left, it's going down. And as it's going to the right, positive infinity for x, our y value, or q of x, is going to negative infinity. It's going down. So when we're talking about x, negative infinity is left, positive infinity is right. When we're talking about y, or whatever our function is, like in this case q of x, if it's going up, it'd be positive infinity. If it's going down, negative infinity. Okay, so here's another one. So we want to know the leading coefficient, the degree, and then we use those two things to determine end behavior. Right, so what's the leading coefficient in this case then? 2. Okay, so it's positive, right? Okay, that's the, okay, knowing that it's positive 2. All right, the degree in this case is 5, and that tells us that it is odd. So if we have a positive leading coefficient and an odd degree, that means then the graph is going to start at negative infinity and end up at positive infinity. What happens in between there, we really don't care right now. All we're caring about is what happens on the ends. Okay? So as x approaches negative infinity, if you have problems with the infinity symbol, you can always turn your paper sideways and write an 8 if you needed to, because that's kind of what it is. So as x approaches negative infinity, p of x, in this case, is our function. That approaches negative infinity. It goes down. Right, so as it goes to the left, it's going down. As it goes to the right, it's going up. So now we're going to look at graphs, and from a graph, determine then whether the function is an odd or even degree and whether it has a positive or negative leading coefficient. So make sure you have that chart in front of you, right? And look at this graph. And so there's 4 different possibilities, right? So you got a 25% chance of guessing correctly. Right? Okay. So if you look at the chart, which is on what page, Jennifer? 453. Right? Which one of those 4 is this graph similar to? So let's see. Let me go back here. Okay. So which one is this closest to? Let's, all right, negative odd. Okay. All right. Everybody agree with that? Okay. It starts at positive infinity. Okay. It starts in the upper right and goes to the lower, or the upper left and goes to the lower right. Okay. So in this case then, we have one that is similar to this one here. So it's like this one. So that means that we have odd degree with a negative leading coefficient. And basically, you want to look at, okay, where does it start? Okay. Does it start in the second or third quadrant? Right? Okay. So this one starts in the second quadrant and it ends up in the fourth. So which of these start in the second and end up in the fourth, and regardless of what happens in between? The stuff in the middle doesn't really matter for what we're trying to decide. It will eventually, we'll talk about that, but right now it doesn't matter. But I would have to say that this is, because it's an odd degree, that odd degree has to be at least 5. The degree has to be at least 5. And the reason I know that is that there are 5 zeros. Okay? So since there are 5 zeros, the degree has to be at least 5 and odd. It actually could be more than that, right? But it would have to be at least 5. Okay? All right, let's take a look at another one here. So which one is this like? Right? Where does it start? Where does it end? Okay? All right, so Thomas, which one is it like? Okay, so it's similar to this one in the upper right corner, right? Okay, all right, it's like this one here. Okay. So it would be an even degree with a positive leading coefficient because they both go up. So on the ends, if all I cared about was, it looks like this. What's that doing? That's smiling, so that's okay. Even and positive. Good. All right. So do both of those two then. Now that we've studied factoring, solving polynomial equations, and end behavior, we can graph a polynomial. Okay? Now, one of the things about graphing a polynomial is that we are going to use our technology. We're not going to get crazy with this, okay? We're going to use the availability of our technology to do this. And now one of the things, there are important features that you must show when you graph, okay? But we're not going to just do it by hand. We're going to use our graph to basically just copy down a graph that we have, but we're going to make sure that we have specifics there. So we want to find the zeros and the y-intercept, plot them on our graph. Now we're not going to make a table. We'll look at some specific points, and we're actually going to do example 3 and example 4. We're going to kind of work them together here, which example 4 talks about finding maximums and minimums. Okay. So then we're going to make sure we have the proper end behavior, go in the right directions then also. All right, so here we have this x cubed plus 4x squared plus x minus 6. Now, when you look at that, there's one thing when I look at that, I know immediately, well, there's a couple things I know immediately, okay? What's one of the things that you can see, you look at that, and when we talk about this table here, all right, the different things they want us to find, what's one of the things you know right away? What? Okay, there could be 3 zeros, okay, because it's a degree 3. Okay, so there's one thing, all right? So there's a possibility of 3 zeros. What else? The y-intercept, what is it? Okay, so I know that I'm going to have, on my graph, I am going to have y-intercept at -6. Okay? All right, what else? What is it? The fact that it's a cubic, okay, so we got 3 zeros because it's a cubic. What else does that tell me? That tells me talks about the end behavior, right? Okay, it says it's odd, so it's either going to start, so this graph is either going to start here and end up there, or it's going to start up here and end up down there, right? It's going to be one or the other, okay? But we know which one it is, don't we? Okay, which one is it? This is an odd degree and a positive leading coefficient, okay? So it's got to start down here somewhere, and it's got to end up there somewhere, okay? All right, do we know where exactly? Not right at the moment, we don't, okay? So, let's go ahead and graph this. Put this on your calculator. It doesn't like me. Okay, you got your graph, and your graph looks like, oh, come on, what'd you do that for? Looks like that, right? You didn't know that you could do that, did you? All the things, all the really cool things you're learning in this classroom. Yeah, I don't know where that was. Get rid of that. Okay, here we go. All right. So the graph looks like this. That's pretty cool, isn't it? All right, now, is that what yours looks like? Okay. So there's specific things that we need to look at then. We can see that there are zeros where at? Where are the zeros at? Okay. Okay. -3, -2, and +1. Okay. So when I graph this on paper, I need to make sure that those are exact values. Okay. Then the other thing I need to know where they're exact. So we've got our x-intercepts and our y-intercepts. Right? But there are these other things that in the book they call them, one terminology they use is called turning points. Okay. Well, when you think about a turning point, if I'm going up and I turn around and start coming back down, what's another name for that point where I'm turning at? What else could I call that? So if I'm going up here, so what's another thing, another name I could call this point right here that I just put on there? What? A maximum, right? Okay. That could be a maximum, and then this one here then would be a minimum, okay? So I need to make sure those points are correct also. So when I draw my graph, I've got to make sure I have my x-intercepts, my zeros, my y-intercept, and then max and mins. And from that information, then I can draw a really good rough sketch. It's still not going to be perfect, but it's going to be a lot closer than it would be if I just kind of threw numbers down there and drew a graph. Okay. Well, does anybody know how to find those max and min points? Okay. Rachel? No, No, synthetic division won't help me with them. But there is one thing that will help you, okay? All right, there's actually two things, okay? Your calculator will do it, all right? But there's another way, all right? So I want you to do this, okay? What is the, everybody has it in their y equals, right? What's halfway between -3 and -2? What's halfway between them? -2.5, okay? So go to hit trace on your calculator and type in -2.5. Now, does that look like that max point? Okay, all right, excellent. All right. And what was it? A little less than 1, right? Okay, 0.8? All right, so pretty close to the point where I put up there. All right, and so that should be approximate. All right, now our zeros here, we have a 0 at -2 and a 0 at 1. And our minimum is between them, right? Okay, so what's halfway between -2 and +1? What's halfway between them? Okay, -0.5. All right, so now type in -0.5 for your x value. And then hit enter. And you probably get a number real close to -6, right? Probably a little bit lower than -6. Okay. No, it's not right on line because it should be right just off the line a little bit because it's at -0.5, right? Okay. All right. So we have 6 points there that we could graph to make sure that we have an accurate graph then. Okay. Now, I told you how to find the max and mins just by using your zeros. Okay. Well, that's a whole lot easier actually than the other way that we're going to talk about doing it also. Okay. But there's our sketch of our graph. Is that find the zeros, mark them on my graph, find the y-intercept, mark that, find the max and min values, any of them that there are, mark them, and draw my graph. Okay? And that doesn't take very long, does it? Okay. So we could also, to find the max or mins, because Emily said, hey, we can use our calculator to do that. And so I'm going to show you how to use the calculator to do that. But if you use the fact that the x value for a max and min is usually halfway between the zeros, all right, then you're going to be golden there also. Okay? The only time that's a little different is if when we have complex zeros, it kind of changes that a little bit. So I'm going to put it in my y equals n and show you how to use your calculator to do the max and min. Now, the one thing about this, our graph here, is the fact that everything's symmetrical, isn't it? All right? This graph is perfectly symmetrical when it comes up, and then perfectly symmetrical when it comes down. Okay, there's no, they go down real nice, comes back up. It doesn't do something like this. It doesn't go up and then kind of do this and then go back up like that. All right, it's even when it does it. And so when it's even and smooth when it does it, then I know that the max or min is going to be right between those zeros, halfway between them. To where if it looks something like this nasty thing I just drew, then it's not going to be that nice of a case. So then when that happens, we will actually need to use our calculator to find it. Right? So I'm going to zoom in here a little bit just so I can see this better. So I'm going to go from -5 to 5 on my x. Change it just so I can see it a little better. Okay? Now, right, so I want to find this maximum value between -3 and -2. So we use our calculator by going to second trace. And we have number 4 there, which is maximum. Well, when they ask you for a max and min, they ask you for boundaries, okay? So that means that if it asks me for a left boundary, that left boundary then has got to be to the left of where that max is. Well, I could use that 0, couldn't I? Right? So you can do two things. You can either take your cursor and just use the arrow key and scroll over, or you could just type in the number like -3. Okay. Anything that puts you to the left of that max point. All right, then it says right boundary. So I could use my cursor and go to the other side of it, or I could just pick a number, whatever I want, and then hit enter. And you notice that here we go, we've got this triangles on our screen, and that max point is now hopefully between them. Right? Now that it's between them, I can hit enter, and it'll tell me that it's at, it wasn't exactly at negative 2.5, but pretty close. Okay, right? Negative 2.53 and 0.879. So by looking at using the zeros like that, we know we're going to be pretty close to where we're at as far as the max or min. Okay. And so now we can use our calculator also. So I would graph this approximate number. Okay, so if we did negative 2.5 and 0.8 or 0.9, all right, that would still work. And to find the max, or the min then, we do the same thing, second trace. Number 3 then for min. And our minimum is down here. Okay. So we could cursor over here a little bit if we want. All we need is any number to the left of that minimum. I could use negative 2 again if I wanted to. I could use that 0. Okay. And then for my right boundary, I could use the other 0. Okay. And then guess. And it says, is it a little bit closer to the x-axis than we thought. Okay. But those numbers that if you use the halfway point, usually they're going to be good estimates. Okay? They're not going to be exact, but good estimates. So here the minimum is negative 0.13 and negative 6.06, okay? Which is very close to what we graphed. All right? So you can estimate your max and min for the graph purposes by going pretty much halfway between, right? Unless it kind of goes off a little bit from that, right? Okay. All right, let's finish this up. And we're going to talk about do max and mins one more time. Okay, turning points where a graph changes from increasing to decreasing or decreasing to increasing. Okay, it stops going up and starts going down, or stops going down and starts going up. Okay? And we call those local maximum and minimums. Okay? If a polynomial function has degree n, then it could have at most, okay, n minus 1 turning points. Okay? In other words, it might, if I have degree 5, I could have 4 turning points. If I have degree 3, I could have 2 turning points, okay, at most. Right? If I have degree 12, I could have 11 turning points, and that would be a pretty interesting looking graph. But I could have exactly 5 zeros if it's a 5th degree, or 6 zeros if it's a 6th degree. So here we're going to use our calculator to estimate maximum and minimums. Right? So put this 2x cubed minus 18x plus 1 in your y equals. Now, in our typical standard viewing window that we use most of the time, unfortunately, we can't see the max or the min. So what do I need to do so I can see them? Okay. Need to zoom out, which means my y min and max need to become, I need a lower min and a higher max, right? Okay. So we can go to our window, and let's try negative 20 to 20. Right? So I've basically doubled the size of my window vertically. Graph it, see what happens. I can see the min, but not quite the max, right? So I'm going to make my y max a little bigger. We'll go to 25. That's better. Now I can see them both. And so then we're just going to use that feature, that calculation feature, by going to second trace and number 3. We'll do our minimum first, I guess, in this case. Now, the minimum is down here on the right, okay, in the fourth quadrant. So it's between these two zeros I can see, isn't it? So I can use those two zeros, or I could use anything close to that as my numbers. So if I use 0 as my left boundary, I could use, it looks like this other 0 here is at 1, 2, 3, at about 3. So I could use 3 as my right boundary. And then I know that's the only minimum between them, so I can hit enter there, and they tell me that my minimum is at, well, I have 1.73 for x and negative 19.78 for y. Now, when we're talking about max and mins, we are only talking about the y values. We're not talking about the points. We're talking about the y values. So my response here then, when I write my answer to this on my paper, so my minimum, I will say the minimum is approximately negative 19.78. And I want you to use 2 decimal places. Okay. The minimum is approximately negative 19.78. It's just the y value, not the point. Okay. So then we find the maximum. So we go to calculate, or second trace again. Number 4 for maximum. Okay, we want to be to the left of that max, which looks like negative 3 would put me to the left of it. And then I could use 0 again for the right of it. Since it's between them, I can hit enter. And so here's what the graph looks like for the max. So I would say the max is approximately 21.78. And that would be my answer. So the minimum, that number, maximum, that number. We're not using the x values. Anybody knows anything about those x values? Okay, yeah, after the decimal place they're the same. One's positive, one's negative though, right? Okay. Sometimes that happens. Right? That's actually the square root of 3. I think it is. Let's just take your calculator and do square root of 3. Yep, look at that.